We'll now go through our set of nomenclature questions. Part A of this question is a bicyclic molecule. So we know that that's the first part of the name. We'll figure out our 3 bridges after. If we count the total number of carbons in the bicyclic system, we'll see that there's a total of 9 carbons. So we know that this is a nonane. And then we'll highlight our 2 bridgehead carbons in pink. So we have 3 paths in a bicyclic molecule. This first one that's in green. That first chain contains 3 carbons. We'll highlight our second chain here in purple. We can also see that that contains 3 carbons. And finally, we'll use yellow for our third path, which is the one in the middle. That contains just 1 carbon, because recall we don't count the bridgehead carbons as part of those. So we have here bicyclo 3,3,1 nonane. Moving on to part B, we have a question where there's a lot going on here. But the easiest piece is to find our parent, and that's clearly the ring. We do have a somewhat long substituent coming off of it, but there's only 5 carbons in that substituent, whereas the ring itself is 8 carbons. So the easiest piece of this question is that our parent chain is the cyclooctane ring. In terms of where we're going to number this, we're going to start on one of the double bond carbons. And that gives us 4 possibilities, which I've highlighted here in yellow. Now we need to choose the one that will have a substituent at that position, because we want to start at carbon 1 with the alkene. So that means we can disregard that position. It has no substituent. If we go to the position below it, that would give us a substituent on carbon 1, but our next substituent would not come until carbon 3. And if we choose the lower alkene, the one at the bottom of the ring, we would get substituents at carbons 1 and 2. So that tells us we can also disregard that position. Choosing either of these last 2 carbons would give us substituents on 1 and 2. But if we choose this carbon here, as we go this way, we also have a substituent on 3. If we start here though, and go around to the left, we don't get our third substituent until carbon 4. So that lets us identify which position we need to start at. So let's get rid of a lot of this. So now we know we need to start here and go around to the right. So we can start naming our substituents. We can see that we have a series of methyl groups, and those are at 1, 2, 3, and 7. At carbon 5, we have bromines, and we list the number twice, of course, because we have 2 bromines. At carbon 6, we have a pentyl group. So now we're ready to start putting this name together. Bromines will come first alphabetically. 5,5-dibromo. So the 4 methyl groups means we need the prefix tetra, but that still comes next because we ignore the numerical prefixes for alphabetizing. So 1, 2, 3, 7, tetramethyl. followed by 6-pentyl. And we'll go down to the next line. This is where we put our parent, cyclo-octa. But we also have to indicate the fact we have two alkenes. We can see that they start at carbons 1 and 3. So this will be cyclo-octa 1,3-diene. But we're not done yet. We can see at carbon 7, as well as carbon 6, we have chiral centers to account for. So we'll need to put that out front. 6 and 7. Now normally for alkenes we would also need to put E and Z in. In this molecule we don't need to do that because it's a cyclic structure, and with rings this small we can only arrange the double bonds in one way. So that's why we don't need to account for E and Z. You could do that if you wanted. It would not be wrong to do that. And just to let you know, if you're looking to try and do that, we'd have 1Z as well as 3Z. But again, that's not something we need to include here. So as we look at each of these carbons to determine stereochemistry, at carbon 6, the bromines over here will make this carbon first priority. We have second priority to the left and third priority up the top. Now that arrow 1 to 2 to 3 is going to go clockwise, but because our lowest priority, the substituent, is pointing forward, we have to take the opposite. So the stereochemistry at carbon 6 is S. At carbon 7, the methyl group here is third priority. We have first priority to the right and second priority going down. Our lowest priority substituent, the hydrogen, is already pointing back. We don't have to make any adjustments. The arrow goes clockwise, and so we have R. So our full name for this molecule is therefore 6S7R 5,5-dibromo 1,2,3,7 tetramethyl 6-pentyl cyclo-octa 1,3-diene. Now we have one more nomenclature question to look at. No longer dealing with a ring, so if we have any alkenes we will have to do E and Z. And we can see though the one piece of this question that's fairly easy is the longest chain goes straight across. Only thing we have to decide is, do we number it starting at this end or at this end? And we do that based on the end that has the pi bond closest to the end, which is clearly this end. So we're going to number this one in this way. So we have a decane derivative here that we're working with. Now we need to go through and name all of our substituents. So carbon 3 is a T-butyl. Carbon 4 is an isopropyl. Carbon 7 has a chlorine. Carbon 8 has an iodine. And carbon 9 has a cyclopropyl. So now we'll address stereochemistry last, and there's going to be a lot of that because we have a chiral center at 3, a chiral center at 4, a double bond at 5, another double bond at 7, and a stereocenter at 9. But we can put our substituents in alphabetical order. 3-tert-butyl, 7-chloro, 9-cyclopropyl, 8 iodo, and 4 isopropyl. Then our parent name needs to include both the alkenes and the alkynes. We can see we have a 10 carbon chain, so this is a decane derivative, so deca. Alkenes come first in the name, so 5,7 diene, because there's 2 alkenes. And then the alkyne, which starts on carbon 1, comes at the end. Now we need to determine stereochemistry. So if we start at carbon 3, carbon 3 is one of the more challenging ones because we're differentiating between a tert-butyl and an alkyne. So the tert-butyl is a carbon bonded to 3 carbons, but so is the alkyne. So we have to go 1 carbon further. This end of the alkyne is also a carbon that we count as bonded to multiple carbons because of the alkyne, where these are just methyl groups. So the alkyne is first priority, T-butyl second, and the rest of the chain is third priority. This goes counterclockwise, and so we have 3s. I'm going to erase those so they don't get in the way as we do the next one. Carbon 4, all of our carbons that are directly attached to carbon 4, the isopropyl, this carbon, and the alkene, count as bonded to 2 carbons. So we're going to have to go further than that. Now, in the case of the isopropyl group, we know that going further just gets us to methyl groups. So that's going to be lowest priority. Going over this way, we then get to the T-butyl as well as the alkyne, which count as carbons bonded to 3 carbons. That's going to be higher priority than the other end of the alkene, which is just going to be bonded to 2 carbons. So again, we go counterclockwise, and we have 4s. Our last stereocenter, which is over at carbon 9, we have third priority being this methyl group. First priority, though, is over here, this carbon, because it's directly attached to iodine, which gives it higher priority than the cyclopropyl ring. Again, counterclockwise gives us 9s. For our alkenes, we can start with this alkene. Clearly, the higher priority substituents here are opposite, which makes it E. And the same thing for the other alkene. Iodine, higher priority than carbon. Chlorine, higher priority than carbon. The higher priority substituents are on opposite sides, giving us E. And a final name for this structure of 3s, 4s, 5e, 7e, 9s, 3 tert-butyl, 7 chloro, 9 cyclopropyl, 8 iodo, 4 isopropyl, deca, 5,7 diene, 1 ine.